All right, welcome everyone. This is episode 6 of Fault Tolerant Friends. So today we have Mohammad Javad Amiri from Stony Brook, who has a really nice paper actually that I've been looking forward to getting presented. So Mohammad, on to you.
Okay, thank you, Sam. So hello everyone, it's a pleasure presenting Bedrock here, and thanks for inviting me. I used to have a lot of details like long introduction on BFT, but a good thing about presenting the stuff people who all are more knowledgeable than me in the BFT domain, so is that I don't need to go through the introduction. So I just have probably one slide on that, where we talk about basically fault-tolerant transaction processing. So basically, as you all know, so we want to provide fault tolerance. We use basically multiple servers. We call them replicas. Each of them maintains a copy of the data. Here, like let's say, a simple key-value store. The client sends the transaction to one of the nodes. We call it the proposer, sometimes the leader. The leader shares this transaction with other nodes. And if majority of the network agrees with that, then the leader commits the transaction, executes this, and tells others to do the same. And we call this kind of state machine replication, a way to realize state machine replication, where basically we have a replicated service, and we assume that okay, all these replicas are deterministic. The execution is deterministic, and the goal, which is the goal behind all this consensus protocol, is to assign some order to this transaction, and then these transactions execute following that order in a deterministic way. So Paxos is the most known consensus protocol, and actually the pattern, if we abstract out the details, the pattern would be kind of the same for most like cache fault tolerant protocols like Raft. We have a node, the leader sends the message. If it receives sufficient votes from basically majority, then it does the commit. And we say that we can tolerate, let's say, at most F nodes out of 2 F+1 nodes. So basically, a majority of nodes need to be alive, like F+1 nodes need to be alive. And since any two quorums, any two sets of voters need to intersect on at least one node, the node that tells others that, okay, what have been decided earlier. So we come up with a protocol with like 2 F+1 nodes. As you all know, it's not the case in the presence of malicious nodes, because malicious nodes can do different things. For example, the most known attack is the equivocation attack, where the malicious node can, for example, tell different nodes different things. The leader in our example assigns the same sequence number 1 to 2 different client requests, or assign the same request to 2 different sequence numbers. So we want to prevent such behavior, such exhibit arbitrary, potentially malicious behavior that basically a Byzantine node can exhibit. And hence, because these Byzantine nodes, these malicious nodes are alive, if we talk about the set of voters, the quorum of voters, we cannot rely only on F+1, because if we have F malicious nodes that vote, that can collude with each other and impact the voting. So we need to outnumber those F nodes. We need another F+1 nodes to outnumber those. So it becomes 2 F+1. So each set of voters, each quorum in our terms becomes 2 F+1 nodes. And again, the intersection of any two quorums cannot be only a single node, because that single node might lie. So we need F+1 node in the intersection. And as a result, the nodes that we need, the total number of nodes becomes 3F+1. PBFT is the most known protocol here. The leader receives a client transaction. It shares the transaction with everyone. And then we add a prepare phase here. What is the goal of this prepare phase? Is basically to detect whether the leader is honest or not. Or in other way, basically, each node tells others that, okay, I have received this message from the leader. Have you received the same message? they talk to each other. And as you can see, the leader doesn't send anything because the goal here is to validate the leader's proposal. And if we see that super majority, or 2F plus 1, which is 2F from here plus 1, that is the leader message, are kind of matching, then we go to the commit phase. We wait for, again, super majority 2F plus 1, and we commit the request and send the message back to the client. Okay, so this is kind of very simple, a very brief introduction, but the problem starts here. So PBFT is not the only BFT protocol that we know. Here I list, I don't know, 14, 15 BFT protocols, but in reality, we have 400, 500 BFT protocols. And if I'm a developer, if I'm an application, I want to use some BFT protocol for my application, the question is, what protocol is the best? This is the question that we had, like, maybe, I don't know, I started working on BFT domain in 2018, and at the point, like 8 years ago, we had this question, which protocol is the best, first, and second, what is the relation between these protocols? Are they coming up with different assumption, different implementation, different design, or can we come up with some relation between them that, okay, if I understand PBFT, it becomes easier for me to understand Tendermint, or from understanding, I don't know, Prime, I can understand another protocol. So this was the question, and at the time I was reading these BFT protocols. We wanted to present a tutorial on BFT protocols. I was lazy. I didn't want to go through all these papers, 10, 12-page papers, like 100 of them. So I was trying to see, okay, if I can find these relations, then maybe I can just read the model, read the protocol sections, and then connect them together and coming up with a kind of platform. And the Bedrock was kind of the artifact from this thing. So we try to come up with the design space, basically the design space for BFT protocols. We couldn't cover all BFT protocols, so we limited to like partially synchronous BFT protocols. And again, our goal wasn't to show a kind of an exhaustive like framework. We wanted to say that, okay, this is a way to model this, to understand these BFT protocols. So we don't claim that Bedrock covers all BFT protocols. We don't claim that it is a kind of a complete, exhaustive framework, but it's just a way of looking at and understanding these BFT protocols. And the way we did that is to coming up again with a design space, saying that, okay, let's say there are different dimensions of designing protocols, and with adding this dimension together, we can come up with a design space. A design space, let's say a 2D, 3D, 20D design space for BFT protocols. So coming up with these dimensions, and then trying to come up with a set of design choices. What is a design choices? A simple definition for a design choice could be looking at as like a function that maps one protocol to another protocol. So I have PBFT, I have Fab. Can I have a kind of a mapping between these two, saying that, okay, if you do this, you can basically transfer PBFT to Fab. So this was the idea. And since it wasn't complete and it wasn't exhaustive, we wanted it to be kind of extendable. So later on, people can add dimensions to this design space, can add more protocols to this design space. And so that is how it is constructed. One more point that I should say here is the paper published in 2024, but it was kind of accepted in 2023. And it covers till 22, I feel like, if I remember correctly. So because we had multiple submissions before getting accepted. So you might see there are missing points here. There are missing important points. For example, DAG-based protocols are kind of completely missing from. So again, we don't claim that this is a completely. But going back to our design space and design choices, let's look at a simple example. Here we have only two dimensions, commitment phases and replicas. So we can have 1, 2, or 3 commitment phase. We can have different number of replicas. And then each point could be a protocol. If the point is green, it means that it is a valid protocol. So for example, PBFT has 3 commitment phases and 3f+1 number of nodes. And then what we mean by design choices is these like lines. So I can, for example, take a protocol as an input with 3 commitment phase and 3f+1 nodes, and basically give you another protocol with 2 commitment phases and 5f+1. So you see, each design choice is kind of a trade-off. Here, there is a trade-off between number of replicas and commitment phases. I reduce one phase of commitment, but I need to add more replicas to that. So this is the way we think about design space. We have different dimensions. We have different functions that are design choices. A quick overview of the system model. We know that state machine replication requires safety and liveness. We know that there is a FLP result that says no consensus can guarantee both safety and liveness, and there are different ways to deal with that. Here we focus on partial synchrony in the Bedrock basically platform. And these are the basically assumptions on the adversary. We know that there is no upper bound on the number of faulty clients, but at most F nodes, F replicas could be malicious at the same point. But these malicious nodes are computationally bounded, so we cannot the cryptographic assumptions cannot be violated. We also know that in the design of BFT protocols, we assume failure independence in the sense that if one node fails, we cannot use the same strategy of this failure. If I'm an attacker and I attack one node, I cannot use the same strategy and attack another node. And it can be done using, I don't know, inversion programming or geodistribution of replicas or other ways to provide failure independence. So before getting to this design space, let's also talk about the different stages that a replica can have in a BFT protocol. Just a review of that, as you all know. So we have clients send requests to the replicas. We have ordering phase, where we basically order transaction. We come up with the order of 1, 2, 3, 4 for the transaction. We have execution phase, where we execute these transactions. It doesn't necessarily be like first ordering, then execution. We could have execution first and then ordering, basically optimistically execute and then ordering. We have view change, where the idea is to change the current node, the proposer, to another one. We have checkpointing, where the idea is to checkpoint messages so that we can do the garbage collection for the old messages that we don't need, old protocol messages. And another basically benefit is that we can synchronize all nodes. And we have recovery. When a node fails, we need to basically recover the faulty node. So in the context of PBFT, if we want to talk about these stages, we have requests received by the leader. We have these 3 phases of commitment: prepare, and commit. We have the execution phase here. Nodes send the reply back to the client. If the leader fails here, R1 is the leader. We have this crumb symbol. If the leader fails, then another node becomes the leader. And then checkpointing happens periodically, every, let's say, 100 messages, every 200 messages. And then we can have the recovery, which is proactive in the context of basically PBFT, and we can discuss that later. So what are the dimensions of our design space? We have at least like 20 dimensions categorized into 4 families. But again, we can think of more dimensions, adding them here, or this is not like, again, complete basically a space. So we divided these dimensions into 4 families: protocol structure, where we have commitment strategy, number of commitment phases, view change, how to do checkpointing, how to do recovery, what is the type of clients, We have environmental settings like number of replicas, communication topology, authentication mechanism, and a dimension related to synchronization, which covers responsiveness, synchronization, and timers. We added two quality of service. We call them quality of service. You can call it whatever you want, like order fairness and load balancing. And there are multiple dimensions on performance optimizations. Do we support out-of-order processing? Do we support pipelining? Do we support parallel ordering, parallel execution? How to deal with read-only requests? Do we have a separate mechanism for that or not? Are we separating ordering from execution? Are we going to use trusted hardware? How do we kind of disseminate requests and reply messages? So these basically performance optimization dimensions, they affect the performance of the system. And the way we collected them is by basically reading papers, seeing that, oh, okay, there is a dimension here that is interesting, we can use it. So it's like, so if you have more papers, then we probably had more dimensions here. So now I'll mostly talk about these three. Don't talk about the performance optimization due to the kind of time limit, but this protocol structure, environmental setting, and quality of service, I try to cover them. So commitment strategy, we said that, okay, there are three different commitment strategies. One is optimistic, one is pessimistic, and one is robust. By optimistic, we mean that the protocol makes some optimistic assumption about either the node, the network, or the failures. For example, we can assume that the leader is non-faulty. The leader is always non-faulty, and then we don't need to check the behavior of the leader at the kind of the main protocol. So we have a kind of the normal case scenario. If we assume that the leader is non-faulty, the normal case scenario becomes basically more efficient because there is no need for example, prepare phase in PBFT. One example is this. We will go through the protocol later on. Another possibility is assuming the backups are non-faulty. If we know that, okay, we have a set of good nodes, 2f+1 nodes that are non-faulty, then we can rely on them to process the transaction. We don't need to send to all 3f+1. Like cheap BFT is one example. And all these optimistic protocols have a kind of a fallback. So later on, they check whether this assumption violated or not. If not violated, then we are happy because we were able to basically come up with a more optimized protocol, more efficient protocol. If the assumption is violated, then we need to fall back to another path, which is probably more longer and needs more kind of checking. Another assumption is, okay, if we have a tree topology, then and all non-leaf replicas are non-faulty, then we can come up with an efficient way. If the workload is conflict-free, what does it mean? It means that, okay, different transactions coming from different clients access different records. Then probably there is no need to order all transactions because the goal of ordering is to make sure that the state is consistent. But if these transactions access different parts of the state, there is no need for ordering among them. If the clients are honest, or if the network is synchronous, then we could have a kind of a better way of designing protocols. Pessimistic protocols like PBFT, they do not make any assumption on failure, synchrony, or data contention. They basically say that, okay, in the normal phase of communication, normal round of communication, we need to check whether these failures have happened or not. And then we have robust protocols that assumes that, okay, the network is under attack, the system is under attack. We need to basically do our best to address all attacks in the normal case scenario. And this is just some way of looking at that. So if we think about failures and performance in the scenario that failure-free, low failure, and under attack, and we want to compare this, so optimistic protocols work best in failure-free, but if we have failure or if the system is under attack, then the performance gets kind of to zero. Pessimistic is like that, and robust is like that. So depending on our network, depending on our environment that we want to basically design this protocol, use this protocol, we need to think about different basically commitment strategies. Yes, is the question?
Yeah, one quick question. If you go back,
Sure.
can you just explain why are you calling this category of this feature, this design commitment strategy? Because it seems like it's just talking about a lot of things, mostly the ordering of the transactions. Are you saying committing to an ordering, or I don't know?
Yeah, I think it could be ordering a strategy as well. But since the commitment is kind of the goal of the ordering phase is to commit a transaction. And I mean, since I'm coming from a database background, maybe that's why it shows commitment strategy. Like, yeah. So committing a transaction, and then it's like, so, but yeah, I believe like ordering a strategy would be a kind of better term, because it's more focused on the ordering part.
Right. Okay. Because these optimizations, as you said, it's a trade-off in performance, but you're not committing to something that could be wrong, right? You always have to fall back. But yeah. Bowen?
Yeah. So I had a question on what do you mean by where the system is under attack? Does it mean, like, for example, I saw the Tendermint was listed under the optimistic strategy. I mean, it has some kind of like a baking, on its assumption or versus assumption that is preventing you from, being attacked, right? And also I saw this curve, because if you go robust, it's like a flat, but if you go to the optimistic, it is like a linear, which makes sense. But I just couldn't quite figure out why it's a flat under robust. So I guess there's some like a definition I don't know about this, like under attack means.
Okay, so that's a very good question. So first of all, this graph is like just showing kind of a relative, basically rate. It's not a kind of an experiment I'm giving showing the result. It just showing the relation between these things. So under different, so it's not kind of such a precise where am I? Precise way. And the reason we had this like Tendermint as an optimistic is more of saying that, okay, we have these assumptions on the time, saying that, okay, we wait for
yeah, that makes sense.
Then but the robots are the ones that in their normal basically normal phase of operation, they add some mechanisms to detect failures, to deal with failures.
Okay, I see.
So the way I think is that, okay, in optimistic protocols, the normal phase of communication, what we do is we assume that, okay, everything is good. And if at the end we fail, what we are going to do is we have a fallback path.
I think I get the sense of all that.
Well, the normal phase is something that it is like it considers everything, not everything, at least some attack scenarios. For example, later on we talk about prime event address order fairness, like partially even in the order, in the kind of the. So that's the way. But I mean, don't worry about this graph. It is just some way of showing that. And
I mean, it's a nice graph. It's bringing up the question. But thank you, I got it.
Yeah. Amir, yes.
Yeah, I know. Again, this is like it's not to scale, and like the graph is not very indicative. But I do see that for like whenever the failure rate is low, like it's like from say at 0, the optimistic protocols are more performant than the robust protocols, but the I guess slope, like the fall off, is pretty steep, I think, once failure started. So is that the trade-off? Like initially, for the robust protocols, I mean, there's some sort of I guess mechanism in which they prevent performance degradation, but that delta still remains. In the case of, say, if there's low failure, it will still perform less than, say, an optimistic protocol at low failure. Right? So is that like fair? Like, is it ever the case that even a robust protocol can outperform an optimistic protocol, like low failure rates? Or
I think hard to tell. It depends on, I mean, because here with like optimistic, there are a lot of protocols that we can categorize in optimistic. So maybe there we can find scenarios that, okay, a robust protocol, even in a low failure, outperforms an optimistic protocol. But the kind of the idea is that because robust protocol in their normal phase communication, the good case latency, they try to deal with failures, deal with attacks, so their good case latency becomes higher, or the normal case scenario becomes more complex. And as a result, compared to an optimistic protocol that makes some optimistic assumption, assume everything goes well, and as a result doesn't try to like address, for example, failures, address contention, address synchrony, then they have a more complex normal case scenario. And this more complex normal case scenario makes the protocol more complex and less efficient if there is no failure. But if there is failure, then this robust still does the same. This robust protocol still does the same thing. Still, all the checkings are done in the normal case scenario, while the optimistic one needs to fall back to another basically protocol, and as a result, it takes longer. But again, this is just a kind of a way of showing that. And if we go to the protocol instances, we may see that, okay, the behavior would be different. I think we have some experiment that hopefully I can show later when we get to that, and we see that, okay, this graph is not 100% true. This is just like a way of presenting this.
But basically, broadly, it's like the upfront cost you pay in order to have some insurance against.
Exactly.
So things go bad, then you're still okay.
Exactly. I think the way you describe is much better than what.
I actually, so I guess to close this, do you have? I've just never heard of these robust protocols. So do you have an example of what one of these five? Like, what is a clear example of what they do?
We will talk about prime. One thing they do is, for example, I think I said that they try to partially address even order fairness. So they have a pre-ordering phase where every node collects all transactions, and then they share transaction with each other. So as a node, I know that, okay, these are the transactions that are in the system. So if later on the leader wants to delay some transaction, or the leader wants to skip some transaction, I can detect that. So these are like type of, yeah.
So it's basically that your mempool is kind of more structured, and you're paying more communication costs in the mempool to know what the other. Okay, that makes sense.
You add more communication phases, and then that helps in detecting such behavior, such malicious behavior. Okay, so we continue with the protocol structure. The next one is number of commitment phases, or good case latency. So it's a partially synchronous network. So we have this GST assumption, and after GST, how many communication phases do we need to commit a transaction? We have view change. Here we target two types of view change. One is stable leader, where we say that, okay, we replace the leader when the leader is suspected to be faulty, like PBFT. We have timers. We suspect that this leader is faulty, and then we replace it. We have rotating leader, where we replace the leader periodically, saying that, okay, after a single attempt, like what AdaChain basically claims to do, which is different from its implementation, but it's like the paper. Or after multiple requests, an epoch, or after insufficient performance. So insufficient performance could be even doing the first one, but this is again another thing that prime does. So prime checks the leader, for example, this leader commits thousands of requests per second. Let's say 1,000 requests per second. If the next leader commits, let's define a threshold 0.8. If the next leader commits less than 800 transactions per second, it means that this leader, maybe it's not a good one. We need to switch the leader. So this is kind of the meaning of insufficient performance. And we change the leader. The next one, which is another phase of another stage of BFT, is checkpointing. So as we said, there is the goal is to garbage collect data for completed consensus instances. We have all this communication, prepare, commit, or any other phases. So while we need the actual transaction and we need the state, we don't need to keep all of them. So after some point, we can kind of get rid of those consensus instance messages. And another point is to restore, we call them in-dark replicas. So let's say some replicas basically were disconnected, or the network was unstable, so they didn't get some instances and they cannot continue progressing. Or sometimes we have in-dark attack by the leader. I'm the leader. I know that we have like these 3f+1 nodes. I know that there is one node that is far from other nodes. So what I do as a leader, as a malicious leader, and if I want to delay the entire system, I try to communicate with only 3 out of these 4 nodes. I mean, 1 plus 2 others. And I choose the far apart node as part of my core. So basically, each consensus instance takes longer time. While if I communicate with those 2 closed nodes, each consensus instance takes basically shorter time. So this is kind of the definition of in-dark attack. And then this checkpointing helps us to recover these in-dark replicas. Recovery techniques, basically, now we detected a faulty node. It needs to be, basically, we need to probably delete the state, apply software, basically recovery techniques, and recover this replica. So how to do that? There are reactive and proactive techniques. Reactive is the one that we are more familiar with. Okay, if the replica is detected as faulty, we basically recover that replica. Proactive is basically saying that, okay, we don't care about failures. Every 2 hours, we recover 1 replica. The next 2 hours, we recover the second replica. So we do this in kind of periodic time intervals, and we do this proactively, independent of failures. And the benefit here is that you don't need to have a failure detection mechanism. So basically, you recover all replicas regularly. Event type of clients are different in these BFT protocols. The most common type of client is kind of requester, which is in PBFT. The client sends a request and receives replies. And sometimes we, like PBFT, we ask the client to collect reply messages and verify them, basically check whether we have F+1 matching reply messages. In some protocols like SBFT, which you are more familiar with, that is we have this task is done by some replica. The replica collects sufficient number of replies and send it to the client. So the client doesn't need even to collect and verify reply messages. Sometimes the client can be a proposer, so it kind of act as a leader, propose a sequence number. So QU is one example, and in general, if we know that the client transactions do not, basically there is no contention in the workload. If we have 10 clients and each client accesses a specific part of the state, then the client can play the role as the leader, because what the client 1 proposes is different, accesses is different from what client 2 accesses, and that's why they can propose basically propose sequence number and act as the leader. In some protocols, the clients are repairer. They try to detect the failure of the replicas and try to even change the protocol configuration from one view to another. So clients could be more active in different protocols. We get to the environmental setting. We have 3f+1 nodes, or we can use trusted hardware, make it 2f+1 nodes. We could have active passive replication with only 2f+1 active, but in general, like 3f+1, we talk about that. We have protocols with 5f+1, or the recent ones with 5f-1, and we have protocols with 7f+1. The communication topology could be different from star to click to tree to chain, the way these nodes communicate with each other. The authentication mechanism, we could use signatures or max or threshold signatures. And then we get to the responsiveness and basically timers. So the definition of responsiveness is that a protocol is responsive if its normal case commit latency depends only on the actual network delay. So in some protocols, basically we assume that, okay, there is a predefined upper bound and we need to wait for that upper bound. Examples are Tendermint or SBFT. The view synchronization is where we do the we do the synchronization between all replicas. Usually it's part of the view change where we want to change the view. We want to make sure that, okay, all nodes are synchronized at that point. And we have different types of timers in different protocols. So for example, in PBFT, we wait for reply. The client waits for reply messages. It has a timer. We want to trigger view change or trigger consecutive view change. It's another timer. In some protocols, we detect backup failures with timer. We do kind of view synchronization or many performance check, all these things with timer. So timer is basically the mechanism that we heavily use in partially synchronous protocols. The next two dimensions are about the quality of service, order fairness. Basically, we want to prevent adversarial manipulation of request ordering. What does it mean? It means that, okay, as a leader, I receive transactions, assign sequence number to these transactions, and send this transaction out to others. But no one can check whether the sequence number, the order that I assign to these transactions is the same with the order that I receive these transactions. If I'm a malicious node, I can change the order of transaction. I receive transaction TA before TB, but I assign TB a lower sequence number. So order fairness tries to basically address this. Load balancing tries to balance the load across different nodes by saying that, okay, usually there is a high load on the leader. So what if we try to basically balance this? Now, having these dimensions, we can come up with different design choices. As I said before, a design choice is kind of a function that maps a protocol to another protocol. So I'm going through some of these design choices. Some of them might be more interesting, some of them are less interesting, but let's discuss them. Yes, Sam.
Quick question. So I just keep thinking in the back of my mind, you mentioned the 7f+1 category. What do you gain from going to 7f+1? Because I know going from 3f+1 to 5f+1, you can go down one round. What do you get from going to 7f+1?
You can tolerate F more failures.
You can tolerate F more failures.
Yeah, if you add 2F, you can tolerate F more. Basically, this is kind of the idea of.
Okay, but that's it. It's only in terms of
yeah, mostly yeah.
I see. Okay, thanks.
Yeah. So we started linear PBFT, which is there is no kind of protocol with this name, but it has been used to construct other protocols as well. So the idea is that instead of any all-to-all communication phase, we can split an all-to-all communication phase into two phases, all-to-one and one-to-all. basically, instead of saying that I send my messages to everyone and everyone tries to collect 2f+1 messages, I send my messages to a single node. The single node collects 2f+1 messages and tells others that, okay, I received these 2f+1 messages. And definitely we need some sort of evidence, quorum certificate, anything to show them. And here is basically one example. So let's say this is PBFT. We have this pre-prepare phase. We still have this pre-prepare phase. But instead of having this prepare phase where all nodes send messages to everyone, they send messages, this prepare to a node, which could be a primary, or if we want to use the term that has been used in SPFT, we can call it a collector. It could be any other node. It collects all these messages and then send all messages to everyone. So basically, we add one phase of communication if we call each message ingoing one phase, but we reduce the complexity from n squared to n, and we can do this the same for commit. So basically, we have a collector. This collector collects messages and send them back to the. So one thing here is that, okay, we need to use signatures because we want to make sure that, okay, these are the correct messages. And yeah, that's one simple design choice. The other one, which is Sam just mentioned, is like reducing one phase of communication by adding basically 2f nodes. So instead of 3f+1 nodes, we go with 5f+1 nodes. But as a result, we can reduce one phase of communication. And why this is happening? Because remember, we had this prepare to check whether the replica, the leader is correct. So this prepare is needed for ordering within a view. If the replica is correct, we can continue. We need this commit for ordering across views. Basically, we need this to check the quorum condition, the quorum overlap across views. So we have a view change quorum, we have a quorum from the within the view, and then we check whether these two intersect on sufficient number of nodes. If I go with 5f+1 nodes and I use 4f+1 as the quorum size, this 4f+1 is sufficient for both within the quorum and across the quorum. So it ensures that, okay, even across quorums, we have at least 2f+1 nodes in the overlap and 2f+1 is sufficient. And interestingly, recently, I mean, like, if I remember correctly, 5 years ago, we had two papers at the same time at PodC conference. They both show that, okay, 5f-1 is sufficient. We don't need 5f+1. And the idea was that if I know if the leader is malicious, I can remove the leader from the quorums that I receive. So basically, I don't count the leaders, basically message. So if I exclude the leader, then there are f-1 faulty nodes. Then the size of the intersection needs to be 3f, and then we can show that, okay, with 5f-1, we can handle this. But we need signature here to know that, okay, this is the leader, and the leader is, this node was the leader. We remove the leader, and then we get this. I mean, the proof is not that difficult, but it's very interesting, basically, thing that, okay, you know who is the leader, you know that the leader is malicious, so get rid of the leader, and then we can reduce. The other design choice is leader rotation. So one way to think about that is that, okay, instead of having view change in PBFT, so view change, what is the goal here? The view change is very difficult, very complex. We need, when we have a view change, we need to start from the last stable checkpoint, collect everything, and check which one is correct, which message is correct, which message is incorrect, and do all these things. But if we do the view change, somehow for every single message, then because all nodes are kind of synchronized, then we only need to check the previous message. Then we don't need to go through all these complex view change things. And this is how kind of hottest stuff, the basic hottest stuff works. So we add this view change at the kind of the beginning of every phase. So we increase the number of communication phases. But what happens is then we don't need any complex view change routine. So this is kind of at the abstract level, this is what's happening. So we have view change every time, and then we don't need the view change to go through view change, complex view change. We can even get rid of the view change entirely by kind of sacrificing responsiveness. So I say that, okay, I wait for sufficient time. I know that there is a predefined known upper one delta, so I wait for 2 delta to make sure that I have received all previous messages. And I assume that, okay, because we are after GST, we are in a kind of a stable network, I will receive whatever has been proposed earlier, and then I can go to the next phase. We have cheap BFT. Cheap BFT has basically 2 versions. One version with trusted hardware, which I'm not going to discuss here. But the simplest version is that saying that if I know I have 2 F+1 nodes that are active, that are correct, so I can continue with those 2 F+1 nodes. So basically, I send my message only to 2 F+1 nodes. Here, F is 1, so I communicate with only 3 nodes. And at the end of the message, I just send the message telling to those passive nodes that, okay, we committed this transaction. So what's going to happen is I reduce some communication here, but if failure happens, then I start with those, I try to make those passive nodes active and communicate with them. So here, basically, you still need 3 F+1 nodes. You cannot remove some nodes from the network, but those nodes, F nodes, are passive. They don't contribute to the basically process. Oh, okay. So it's already 3. Okay, so I should be much faster, I think. So I try to go through the next few ones quickly.
How many more slides? Yeah, is it like quite a lot? Or?
I think I have a lot, but
we can definitely go like over a little bit.
I try to probably discuss some of them briefly and the interesting ones, and then so we have optimistic phase reduction. The idea is that, okay, if all 3 F+1 nodes are active, I mean all 3 F+1 nodes communicate with me, they all are correct, so I don't need to go through the commit phase. Basically, if all nodes are, and this is what SBFT does. So if I receive messages from all 3 F+1 nodes, then I can directly commit. But it needs to change the view change a little bit. But I mean, that's how it works. Another way of looking at is that, okay, if only non-faulty replicas construct the quorum of response. If all nodes in the quorum are basically coming from non-faulty replicas, then again, I can remove one phase of communication. This kind of optimistic assumption goes even beyond that. We have Ziziwa. Ziziwa tells, okay, if I assume that the leader is correct, all nodes are correct, then the leader orders and everyone executes and send the reply. There is no need for any other communication. And if something goes wrong later, for example, the client doesn't receive 3 F+1 matching messages, then the client tries to tell us that, okay, see, I have received non-matching request. Something goes wrong with your protocol. And then we try to go to the basically a slow pass fallback and address this. So this is kind of somehow the most kind of the lower bound of BFT protocol. So you have order and you execute. This is the most optimistic way of looking at it. So you order, execute, and if something goes wrong, then the client tells us, and then we try to resolve that. HQ says that, okay, if there is no conflict between requests, if requests coming from different clients and if they access different parts of the state, then probably we don't need ordering. Every client becomes basically every client becomes a leader. It tells that, okay, execute this, and they all execute and send a reply back. So here I'm talking about the normal case scenario. Then they all have a fallback. What if this doesn't happen? So ZZivo has a version, ZZivo 5, which is kind of the resilient version. It adds 2F. This is kind of the logic behind 7F plus 1 as well. It adds 2F plus 1 replicas, but with doing that, it's able to tolerate F failures. So if you remember in ZZivo, we said that, okay, everyone needs to contribute. Everyone sends the same reply back to the client. Here we go from 3F plus 1 to 5F plus 1, but the client only needs to wait for 4F plus 1. It doesn't need to wait for all 5F plus 1. So that way, it kind of provides some resilience. We have authentication. We can use max signature or threshold signature. Sometimes we cannot use, for example, for linear protocols, we cannot use max because we need non-repudiation. And sometimes we can replace signatures with threshold signatures, so to get a better kind of more efficient protocol. This is what Prime does. Going back to our discussion at the beginning of the session. So the Prime, you see, it adds all these 3 phases, kind of adds a BFT protocol before the BFT protocol to basically, and the goal is that all nodes become aware of all transactions that are in the system. And then this kind of pre-ordering stage helps us to, now I know all the transaction, and I can check the behavior of the leader, whether the leader basically orders them correctly or not. And by correctly, I mean, it doesn't mean that, okay, it completely provide order fairness. Also, the communication is similar to what order fairness protocols do. But if the leader skips some transaction, the nodes can detect. And then we have order fairness. Here, I add Themis only because it's based on Hotstop, but there are many order fairness protocols. And then they do this, like, again, local ordering. Each node locally order transactions. Basically, I should say in this way, client communicates with everyone. Client sends the request to everyone. Every node collects a batch of requests, locally order them, sends back to the leader. The leader collects all these locally ordered batches, and then coming up with a fair order that is acceptable by all nodes. And fair order here, there are many definitions of what is a fair order, because as we all know, so different replicas might receive these transactions, this client transaction in different orders. So even if all of them are honest, we might coming up with different orders. So that's why this global ordering by the leader is a bit kind of difficult.
Bowen here has a paper on this, and actually so Bowen did his PhD with Sriram, and basically Bowen's colleague Shaubik is the author, the main author behind Themis. So it's interesting that you're presenting this.
Oh, perfect. Yeah.
Oh yeah, I'm a big critic of Themis, so but it's good. I mean, there are a lot of definitions, which I totally agree.
Later on, we try to come up with something based on Themis. Basically, we had a concept of data-dependent order fairness, and our idea was that, okay, we don't need to order all transactions. We only need to order transactions if they access the same data, the same resource, something like that. And if we kind of make them kind of this limitation, remove this limitation, then we can make it more efficient. Because the problem with the order fairness protocol, at least this style of order fairness, that we need to first of all, the client needs to communicate with everyone. Everyone needs to coming up with a local order. Then they need to share these local orders with the leader. The leader needs to go through all these graphs and coming up with it. So there is a kind of overhead here. But if we can reduce this overhead a little bit, would be interesting. So, and then there is an idea of having a tree-based protocol. So it's for the purpose of load balancing. So it says that, okay, there is a basically there is a high load on the leader. The leader needs to receive all these transactions and go through all these phases. So what if we want to make it more balanced? So what they do is they, in Cari, which is an interesting protocol, they kind of construct a tree structure. They say that, okay, we have the leader. The leader, let's say the leader has 2 child nodes, N1 and N2. Each of N1 and N2 has 2 children. N1 has N3 and N4. N2 has N5 and N6. And the way it works is that each phase, we divide each phase into H phases, where H is the log N, basically the height of this tree. So you see, for example, the prepare here, instead of going from the leader to everyone back to the leader sends it to its child nodes. The child node, each of them sends it to its own child. And then we collect back these messages. So this way, we have a lot of communication phases because we divide one to H, but then we provide load balance. So what they showed in the paper is that if we add pipelining on top of these, we might be able to kind of reduce the overhead and we might be able to get some good performance. But this is also an interesting, if we want to provide load balancing, this is one way to do that. And while we basically exploring this design space, we were able to come up with some other protocols as well, basically some unexplored point in the design space. Might not be very interesting, but we kind of combine the fast BFT 5F+1 with this tree style. And this was kind of another protocol to say that, okay, we have a lot of communication phases, how to reduce these communication phases in the tree-based tree. So we can do, instead of 3F+1, we can do it with 5F+1 or 5-1 actually, and then reduce these communication phases. So we kind of provide load balancing with the same number of phases as, for example, hot stuff. And this is kind of if you want to have an overview of what is in it. Some protocols have pre-ordering, and then we have prepare, and commit. We use the kind of the PBFT style. But like, for example, Ziziva has reduced this. And these are for the fallbacks, I mean, these hashed styles. And yeah, see, so you can see. Or for example, you can see in hot stuff, we have the view change phase first, and then we have the ordering, and then the execution. And interestingly, hot stuff, because it does it every single message, then there is no need for checkpointing in some way. Because checkpointing, the purpose is to synchronize all nodes. But if we do the synchronization every single message, then there is no need. With all of them, then we were able to get to our goal, which was having, okay, we start with PBFT, we can have some functions, and exploring these functions, we can go from one protocol to another protocol. So I don't think these are like important. Again, this is kind of summary of what we have. And a little bit about the implementation. So we try to implement all this like platform together. So definitely once we get to the implementation detail, we couldn't cover, for example, all protocols. So for each part, we use one protocol as the default and follow that pattern. And then what was interesting for us is we were able to come up with a kind of a simple DSL. Kind of, it's more of a protocol config file that we present a state transmission in that file, saying that, okay, this is the phases, these are the states, these are the messages that we have, and then what are the transitions? It's longer, but here is what. From the client, the state is idle, I go to this state, I change the sequence number. So, and then our implementation is kind of a big, you can see it as a big state space where it covers all protocols. And using this DSL, we know that, okay, what state we should explore. And then this helps us to coming up with, like, for example, with like probably 100 lines, we can have a ZZIVA protocol. 200 lines, we can have a BFT protocol, because we had this state space. And so this is just like write this and it executes. There are still some holes in that implementation. I was developing that, and since I was lazy, and then I had another student to work on that, but I'm still like, it's not the vision that we had, but it shows some promising results. I don't think I have time to go through this, like, basically experimental results. I can share the slides with you, so that might be helpful. But I just want to add a little bit, like 1 minute, on what we have done after. Oh, okay, so should I continue, or it's like 1 minute?
Oh yeah. Okay.
Sorry. So the experimental result that we had was basically there is no best protocol. Each protocol is good for some scenario. And what we tried later in BFTBrain was to use basically machine learning, a simple reinforcement learning algorithm, to switch between these protocols at runtime. We had a kind of a small number of protocols: ZZIVA, BFT Prime, BFT Hot Stuff, and PBFT, and we tried to switch between them at runtime, and we got some interesting result that, okay, we are able to switch to the best protocol at each point of the time. So, okay, this is just some interesting kind of future work. Yes, Amir, please.
Yeah, so I was just curious, like, how easy is this to extend to like new, like, consensus algorithms that may come out? Because they're coming out almost, like, quite regularly. I think it's like,
right, yeah.
So yeah, I was just wondering how you can like extend to like keep up with the pace of new stuff.
Okay, so that's a very good question. So I think our hope is that by adding more dimensions to this design space, we can at least cover partially synchronous BFT protocols. Even we try to kind of model DAG-based protocols, and we had some promising results. I mean, we were able to somehow capture DAG-based protocols. There are many details that we have it's kind of abstract out, right? So some of the details are not constant, but at least at the high level, it is feasible, I feel like. Again, we might need to add more dimensions and a little bit abstract of some details, but we can do that. And at the implementation level, it is a bit more difficult. While the current way we had this implementation is that we have a plugin manager, which is for a specific protocol-specific behaviors. You can add some kind of protocol-specific behavior in the plugin manager. And then we had this kind of a state manager where our idea was to kind of enabling developers to add more states there easily without need for kind of even recompilation of the protocol. But it's hard to tell, and yeah.
Thanks, Mohammed. This was really nice, actually. It's too bad we didn't have like an extra hour. I really like the DSL approach. I'm kind of, so one question I was having while you were talking is, I'm personally, at least in this moment of my career, super interested in optimization and anything related to like speculative execution. It seems like there's a lot of different, it seems like each paper that you presented has one or two, like the speculative ordering, or the other one will do speculative execution, and some of them will. Can I just in the DSL say like, hey, do all of these, right? Like, or are some of these optimizations kind of, do they fight, are they kind of not orthogonal, but do they have some dependency that if you use one, you can't use the other one for some reason? Or
I think the DSL has the we can have some sort of like, if we know whether they can be compatible or not, then we can describe this in DSL that, okay, if you go with this decision, then you are not able to handle others. But yeah, but I think we haven't tried that, honestly. So some of the others.
But just at a very high level, if you go back to your, so where you have that diagram with this one.
Yeah.
Not this one, sorry, the previous one.
Oh,
yeah, this one. So, this is still pretty sparse. It's like, oh, we start with BFT and then we can add one or two features and directions, but can't, like, what would be I think an amazing kind of learning tool for people learning about these is just go to the DSL, then okay, I'll add like feature 3, 5, and 7, and then like I'll get a syntax error like, oh, you cannot do that because blah blah, this feature doesn't work with this one. So what I'm wondering is, at a super high level, like, are these features, I mean, they're definitely not all orthogonal, right? But let's say we focus just on the optimization ones. How kind of independent are they? Or is it not possible to basically apply all of these optimizations, right? The 6 or 7 that you're listing.
Okay, so that's a good question. So two things. One is that some of them are not compatible with each other. For example, some of these optimization are on top of like 3F+1 family of protocols. If you have a protocol with 5F+1, then you cannot. Okay, this is the kind of, but there are more. And in terms of optimization, this is the same as well. So some optimization can be done on even the performance optimization on top of a specific group of protocols. This is one. The second one is we don't have the kind of the verification part on top of DSL or checker part on top of DSL. We plan to actually add that, so that basically it kind of, if we do that, the idea is that, okay, it can systematically explores all the space, and then it can tell us that, okay, there are in general 1,275 different protocols that you can coming up, but we don't have it. But again, we think it is possible to do that, because for each of these functions, we know that, okay, what is the input, what are the constraints, what is the output, and then by matching these constraints on input and output, we could, if we have a good list, basically good complete list of constraints for each input and output, then we could coming up with the kind of exploring the types list.
Thanks. Yeah, that would be super awesome. Any other questions? Manav, Aisha, Bowen.
Yeah, pretty good.
Yeah, thank you.
Yeah, thanks a lot. This is actually super nice. Are your slides public? I would love to post them and make.
Yeah, sure. I'll send this version to you.
Awesome. I really appreciate the diagrams that you have for, especially again focusing on the optimization. But I think it's been really nice to just see a very simple kind of phase diagram like this. What does this optimization give you in terms of reducing the phases at least, or changing the kind of topology? It's super useful. First time I see this.
Thank you. It was great.
All right. Well, thanks a lot.
Yeah, thank you for inviting me, and it was
Yes, thank you for the.
Thanks everyone for.
Bye.
Thank you.